The circuit shown here is known as circulator amplifier realized with three op-amps, op-amp 1, 2, 3, and it has three ports. A port that has current I1, V1 here, port that has current I2, V2, and I3, V3. It's interesting, this is stating that the current at port 1 is depending on the differences of the voltages at the other two ports. I1 is V2 minus V3 divided by R. So I1, V2 minus V3, and then we are saying I2, the current at port 2 depends on difference of voltage at port 3 and 1 divided by R. R is the common resistor throughout the circuit as the circuit parameter. And finally, I3 is depending on the voltage differences between the two other ports, V1 and V2 divided by R. As if we are circulating, I1 depends on V2 and V3, I2 depends on V3 minus V1, and I3 depends on V1 minus V2. So no wonder we are saying it's a circulator circuit if this is true. Let's see if this is true. Okay, so assuming that the supply voltages of these op-amps are properly applied, so that they are properly biased, all the three op-amps, no op-amp in saturation, all of them operating in linear region, ideal op-amps, and assuming that the negative feedback is dominant compared to positive feedback, then we can say in this circuit, all the op-amps are stable, linear region, and as a result, virtual short, which means the voltage at negative input terminal and positive input terminal for each op-amp should be the same. So we have V1, you should have V1 here, and we should have V1 here as well. We have V2 here connected, so we should have V2 also at the negative terminal. We have V3, and we should have V3 here as well. Now I'm going to write a very quick, simple KCL at negative input terminal of op-amp 1. The current that is coming this way via R, so let me just make sure that it's not confused with other current. I'm talking about the current that is coming this way through R should go through the next R in series because nothing can go through the input terminals of ideal op-amp that has infinite input impedance. So that current has to go through R as well. Therefore, the voltage drop across these two resistors would be, let's say, if I name this node Vx, and if I name this node Vy, and if I name this node Vz, which is also repeated here. So I have also mentioned Vz here as well. That is just a copy of that Vz at the end via this wire that is connecting the output of the third op-amp to the input of the circuit. Okay, then Vx minus V1 divided by R. So a KCL basically at KCL at negative input terminal of op-amp 1 says Vx minus V1 voltage at the negative terminal divided by R. That is the current going through this resistor shown here should be equal to V1 minus Vz divided by R. V1 minus Vz divided by R. So these two R cancel out from both sides, and as a result, what we get is 2V1 equal to Vx plus Vz. That is very interesting. So we are seeing that V1 is the average of Vx and Vz. And remember, V1 is here, Vx is output, and Vz is input. So voltage at this point will be the average of the input-output voltages. With the same logic, without loss of generality, you can say the same thing about the two other op-amp. 2V2, 2 times voltage here is the average of, is equal to the sum of Vy and Vx. So it would be Vy plus Vx. Okay, so that's another interesting relationship. And finally, you can say the same thing for V3. 2V3 should be equal to Vz plus Vy. Vz plus Vy. Okay, that is interesting. We're going to keep these guys. Now, let me use the differences of these equations. So let me refer to this as equation 1, equation 2, and equation 3. And I'm going to use a different color. Now, let me write 1 minus 2. So if I do 1 minus 2, what I get is 2v1 minus 2v2, so it's going to be 2 times v1 minus v2 is equal to Vx plus Vz minus Vy minus Vx. So I'm going to get Vz minus Vy. But at the same time, Vz minus Vy is the voltage drop across series of, I'm going to use a different color so that it's clearly shown. You can see that the current that flows from Vz through resistor R has to go and continue through the other resistor R, because as I said, nothing can go through input terminal of ideal op amp with infinite impedance in linear region. So therefore, these two resistors are in series with each other when the current flows through them. So therefore, Vz minus Vy, Vz minus Vy is simply 2 times R times I3, because this current I3 should be the same current on top, because these two resistors, meaning R and, let me use a different color so that it's clear what I'm talking about. So these two resistors, resistor R shown here and resistor R shown here, they are effectively in parallel, because on one side they have, on one side we have, for both of them, on one side we have Vy, as you can see, for both of these two resistors. On the other side, they share V3. They have voltage V3, both of them. So the voltage drop across these two guys are exactly the same as if they are as if they are parallel. And since they have the same resistor and the same voltage drop, therefore they have the same current. And if that lower one I3 is going, the upper one I3 as well. So in summary, I can say Vz minus Vy, Vz minus Vy is 2R times I3. Okay, very interesting. So I got 2 times V1 minus V2 is 2R times I3. So 2 cancel out from both sides. And what I get is exactly what I wanted. V1 minus V2 is R times I3, which is exactly matching one of the three equations that I was chasing to find, this one. That's exactly saying what we just found. Now let's subtract equation 3 from 2. So I'm going to just do equation 2 minus 3. Let's see what I'm going to get. So 2 times V2 minus 2 times V3. So 2 times V2 minus V3 is equal to Vy plus Vx minus Vy minus Vz. So it's Vx minus Vz. Now, interesting. Vx here minus Vz. Oh, okay, so it's exactly same as what we saw for the third op amp. Whatever current flows this way, which is same as I1, for the same reasons that I discussed, that current is going through the series of R and R to generate Vx minus Vz. So Vx minus Vz is 2 times R times I1. So 2 times R times I1. Again, 2 cancel out from both sides, and as a result, we get V2 minus V3 equal to RI1. Exactly the same, one of the three equations I was chasing, this one. So the last one, of course, is obtained by doing now subtracting 1 from 3. So it's going to be now subtracting 1 from 3. So 3 minus 1 will give me 2 times. So V3 minus V1, V3 minus V1 equal to Vz plus Vy minus Vx minus Vz. So Vy minus Vx. Interesting. Similar to what I showed you in the two other two earlier ones. Now we're talking about uh, now we're talking about these two, Vy minus Vx. So that means this same current that is going through the series of these two resistors, which has to be equal to I2 for the same reasons discussed. So 2R times I2 is Vy minus Vx. So Vy, Vy minus Vx should be equal to 2 times R times I2, which again 2 cancel out from both sides of this equation. And as a result, what I get is V3 minus V1 is equal to R times I2. That is a super interesting outcome, confirms what we thought is true for the relationship between current and voltages of the three ports in this circulator amplifier. And it's a very remarkable feature as long as you can keep this operation and design in linear region for all three op amps. This is valid. And there are very interesting practical consequences. For example, this whole circuit in a separate video, I'm going to show that this whole circuit can work as impedance converter, can convert a capacitor to an inductor. In a separate video, in a follow-up video, I'm going to show you that if we think of this whole circuit as a circulator that is usually, let's say, indicated like this, so indicated with the direction of circulation, because I1 depends on V2 minus V3, so that's why we have this counterclockwise direction of circulation. So if I have port 1 here, if I have port 2 here, as is shown, and if I have port 3 here, I'm going to show you that if I apply V1 here at port 1, and if I connect a cap C between port 1 and 2, and then do not apply any voltage at port 2, then if I just try to see what impedance I observe between port 3 and 1, it acts as if I have effectively, I can show you in a separate video that with this circuit, assuming inside this circle, I have the circuit shown. So this circle means the circuit that is shown here. Then what is measured between port 1 and 3 behaves as if you have a floating inductor between port 3 and port 1 in this circuit. And that's very interesting. So that's one of the practical ways to come up with a floating inductor. Floating meaning that the two nodes of inductor are not connected to ground. It's a floating between port 1 and between node 1 and 3. But this is a practical way without having an inductor from a capacitor effectively, which is this gap, coming up with a floating inductor. And that's really practically interesting. I will show this in a separate video. I hope that this is helpful.